These are kind of funny. They all kind of return to the center point where they are. Let's see them all come back here. Okay, I think we waited long enough. I'm going to do File New here, and we're going to start fresh. So File New, we'll start in a nice empty space. Okay, so what we want to do is we want to build basically an object that on its own has all the behaviors of kind of following a flock, basically following its neighbors. And so whenever you have an algorithm like this that you want to write and you're thinking, oh, flocking, I've heard of this before, but I don't fully understand maybe what it is, or I need to read more about it, you know, the best place to go is Wikipedia. And that's a good place to start when you want to write an algorithm like this. Just to do flocking, Wikipedia, and then we look at this flocking behavior. And so if we read this article, we very quickly get down to these flocking rules. And there's really three main rules that determine how a flock behaves, and it's separation, alignment, cohesion. So separation is just kind of making sure you don't bump into your neighbors. Alignment is kind of always flying toward where everybody else is going, and then cohesion is kind of staying with the group. And as they say here in the Wikipedia article, these simple rules, the flock moves in extremely realistic ways. So what we have to just do is we have to just implement these three rules. And so let's see how to do it. So the first thing I'm going to do is I'm going to build an object that's going to represent our bird, or object that's going to flock, or herd, or whatever that might be. We're going to be building our unit. And this can obviously later on be whatever we want it to be. For the purposes of this example, we're going to start with a sphere, and then later on we'll make it something that has directionality, so we'll be able to see where it's pointing. So this is our object that is going to flock. The other thing we're going to want to do is we're going to create a group for this, and so that all of our flocks live in a specific group. And this ensures that we can then find them all together, and we can kind of exclude other objects that might live in our space. So I'm just going to hit Control E on this, and when I do that, it puts a group around this thing. It puts this in a group. So if we look at here on our hierarchy, we'll see that our group, which I'm going to rename now to flock, our group. This is our flock group, and it contains our individual flock element. We can call this our I'm just going to say elements. Just keep it really generic, because it could be a bird, it could be something else. So we now have a group that contains a single element. And then what I'm going to do is, so that we can look at the behaviors with respect to one another, I'm just going to create one shared copy. And to do a shared copy, I'm going to hold down Control and Alt. And the reason we want to create a shared copy is it allows us to edit the code of one, and it will automatically apply on the other one. So shared copies share all of the same properties, including script. So now we just have to write script in one, and then they will all use that same script. Okay, so now I have our two objects in our flock. And these are actually objects that are going to have rigid bodies, so they're going to move with physics. In fact, we're going to use physics forces to move our flock, which will be nice, because then it can crash into other physics objects and adapt itself around it and kind of navigate its way through the space. So because our world here has gravity, we want, since our flock will start off with like a flying flock. So what we want to do is we want to counteract gravity, basically. So I'm going to select our flock element here, and I'm just going to I'm going to create a constant force on it by setting this to positive 9.806. This will counteract gravity, basically. So now it'll float wherever we happen to stick it in the space. So now we have this nice kind of floating object that we can now inject with forces to kind of control it with respect to these flocking behaviors. Okay, so let's go to check out the Wikipedia article again, and let's look at the first thing that we need to do. We need to do separation. So this is avoid crowding our neighbors. And so that's the first thing we're going to do. So I'm going to click on our element here, and I'm going to click on the events group of the root unit, and I'm going to click on onTick. So an onTick is just code that runs every frame. So every frame, it will call this code. And that's what we want, basically, because every frame, we're going to look at our neighbors, and then from that, we're going to determine how we move, how we adjust our position based on our neighbors. So, and so this is the perfect place to do it. So the first thing we're going to have to do is we're going to have to gather all of our neighbors. We're going to have to find all of our neighbors, which in this case is just one. Or actually, it's going to be two inside this flock. But from the perspective of this item, we're only going to have one neighbor. And so we're going to have to gather our neighbors. So what I'm going to do is we're going to get our parent node. So self get parent node. And that's going to be, again, our parent. This is the flock group. And once we get our parent node, we're going to get its children, get child nodes. And we're going to store those in a table. So we're going to have to initialize this table here. And then we're going to grab all of our children, all of the nodes that live in our flock group, and we're going to store them in this table. So now we can kind of iterate over this table and look at each one and calculate those constraints that will satisfy that Wikipedia article. So I'm just going to loop over all those elements, all of our neighbors, by using this little trick, with this little standard syntax here, for starting at the first item to the total number of items in our table, which contains all of our children, all of our flock neighbors. And I'm just going to store each element. I'm going to pull it out of the table to make it a little bit more legible and store it inside this element variable. Now the first thing we're going to want to do is we want to remove ourselves from the we're going to remove ourselves from this list because we don't want to look at ourselves when we're trying to determine our neighbors. We only want to look at our neighbors. And so how do we do that? We just simply say if lm does not equal to ourself. So that just simply says look at everybody else minus ourselves, because this table again is going to just be filled with all the elements that are inside this group, which will include ourself, right? This is where the script lives right now. It'll include ourselves. So we got to filter ourselves out. Okay, so let's look at back to the Wikipedia article. First thing we got to do is avoid crowding our neighbors. So we're going to look at all the other neighbors, and we're going to look at our distance from that neighbor, and then if we're too close, we're going to kind of move ourselves away from that object. So our neighbor is going to be ln. We're going to get its world position, and we're going to subtract it from our position, our world position. So now we have basically, we're going to store that in our v delta, v neighbor delta. Neighbor delta. So this is just a variable. We can call this whatever we want. I just called it neighbor delta. So that's basically, think of that as a vector that connects the two center points of our objects in this case. So what we want to basically do is we know we're starting to overlap when that distance between those two center points is less than 2 times the radius of our spheres in this case. So again, here it's equal to 2 times the radius, right? That's one radius is from there to there, the other radius is there to there. When it's less than that, we know we're overlapping, and then we're going to inject some forces to kind of move us away. And I'm just going to hard code in these radiuses. If we look at our sphere, we can see that our sphere's radius is actually 0.31. I'm just going to set 1 as a radius. That means it's not even, they're going to actually start to move away from each other if they kind of move within kind of a bubble around our sphere, which will be a little bit nicer. So I'm just going to say, I'm going to look at the distance between them, and that's just equal to our v neighbor delta length. So that's our distance between them. This returns a number. This returns a vector 3. That's the representation of the line between the two, basically the vector between the two. And this, by getting the length of that vector 3, we get the distance. It's just a single value. That's just literally the distance between those two, which in this case is in meters. Our world is kind of calibrated around meters. The scale of things are in meters, basically. So that's going to be in meters. And we're just going to say if our distance happens to go less than our radius, which our neighbor radius squared, times 2, or diameter basically, then we're going to inject our force that kind of moves us away, or our force that kind of ensures that they don't kind of overlap. So I'm going to just, since we created a new variable here called radius, I'm just going to define it up here. I'm just going to set it equal to 1. So in this case, it's just if it's less than 2, basically. And so we're going to inject a force. Since we're dealing with physics, we're going to always work with our physics forces. So we're going to look at ourselves, and we're going to get a rigid body, and we're going to apply a central impulse. Apply a central impulse. And the impulse we're going to apply is going to be basically the delta of this, right? It's going to be relative to the vector that we've calculated, but we're going to normalize this first. I'm going to normalize it out here. So by normalizing it, what happens is it squashes it. It removes magnitude. It removes distance, and it puts it into a unit sphere. Sphere. So basically, it turns into a normal that has no magnitude. So it's like a direction only. So basically, what we're saying is we're always going to inject a direction, which is move us away from that neighbor times some scalar constant, and we can adjust this. So in other words, the higher this number is, maybe the faster it moves away from our neighbor, and the lower the lower it moves away from the neighbor. So I'm going to also declare this up here. Now we want our scalar to be, and we've kind of introduced this in a previous lesson, we want our scalar to be relative to the amount of time between frames. So the thing about this onTick function is that this gets called every frame. So in other words, if our frame rate is 200 frames a second, this is going to get 200. This is going to get called 200 times a second. And if our frame rate is 10 times a second, it's going to get called 10 times a second. So it means when we're injecting these forces to prevent us from hitting our neighbor, we're either going to do it 200 times a second or 20 times a second. And that's no good. So that means at a much higher frame rate, it's going to be much more forceful than if it's a much lower frame rate. So we just need to make sure that we scale all of our impulses and forces that we're adding based on the time elapsed between frames. And so we do that by saying self get space. That's our parent space. Each space has a timeline, and the timeline has a function called get time elapsed from last tick. So that's the amount of time that's gone between the last time this function was called and the current time the function was called. And I'm going to return that. I'm going to convert that to seconds. So our scaler now scales based on our frame rate. Scales based on the actual time between frames, and not. And we don't just multiply by an arbitrary value that will increase if our frame rate goes up. So now we have a nice clean value that we can kind of multiply that will scale nicely as our frame rate changes. Okay, so let's see what happens if we hit play here. So again, we're looking at all of our neighbors minus ourself, because we're not going to repulse ourself. And if it happens to kind of encroach our diameter, our bubble that surrounds our object, we're just going to apply a force that kind of will move us in the opposite direction, will repulse us. So the order of operations here matters. By subtracting our element from our self, we're going to get a vector that, actually we probably want to reverse this. That will now move us away, and see what happens. Oh, there we go. So now, as they overlap, as you see, if I grab this now and I move this kind of close, it's going to kind of repulse that one like a magnet. Maybe what we'll do is we'll scale that down just a little bit. We'll do 0.5. We'll do half that. It's a little weaker now, the force, and maybe we'll reduce that radius a little bit. It's kind of big. Let's do half the radius. Again, we could read this from the actual sphere, and then add maybe a little like value off of that. But for the purposes of simplicity here, I'm just going to hard code that. So now as we move it close, it avoids it. This one will make that one avoid it, and we've now satisfied that first constraint. So that's good. And so if we make, you already start to see some interesting behaviors here. If I'm going to make more shared copies of this by holding on Control and Alt, and just make a bunch here, and we can already start to see that they kind of are interestingly kind of avoiding each other, and kind of almost feel like there's a little bit of dynamicness there already. Okay, so let's go back to the Wikipedia article. So we've satisfied number one, and I'm going to go into the script actually. Let's document this. It's always important to document it. Sometimes I don't for these tutorials, but it's super important that we do. So this is just this avoid ourself. Don't consider ourself. That's what that if statement does, and then this is to calculate our number one separation. Okay, so we've satisfied that constraint. Number two, alignment. Steer toward the average heading of our neighbors. So how do we calculate a heading? Well, we can look at the linear velocity of the objects, right? So as an object moves, right, its linear velocity is actually a vector 3, and if we normalize that vector, that'll be our heading, basically, our heading. So this thing is moving, let's say this is our x-axis along the horizontal axis of my screen. This is going to be moving with a linear velocity of 1, 0, 0, basically, that 1 being scaled based on the speed of it. So if this was moving at 10 meters per second, it would be 10, 0, 0. If it was moving at 1 meter per second, it's 1, 0, 0. So our linear velocity, if it moves in the opposite direction, it would be negative 1, 0, 0. So our linear velocity is what we can use to figure out our heading. So I'm going to go ahead and let's get the heading out of our element. So I'm going to look at our element. We're going to get its rigid body again, since we're pulling out something related to its physics forces. So we're always going to do that inside the object's rigid body, which correlates to this object right here. So we're right. This is where the code is being run at this level, and we're saying get rigid body to get this thing. So get rigid body, and then we're going to say get our linear velocity. So that's just going to be a vector 3. So our v linear velocity. It's going to store that. But we just want our heading. We don't want to consider the speed, right? We just care about the direction they're moving, not the speed. So in order to flatten out the speed, we just normalize it. And we did that up here as well. This flattened out the normalization we did here, did the same exact thing. It flattened out the distance between those two spheres and just gave us a direction so that we could then move away in that direction. So we've now flattened out the speed, and now we just have to calculate an average. And so to do that, I'm just going to initialize our average heading up here. we're going to store that initially. When you calculate any average, you want to make sure your initial value is 0. And we're just going to say our average heading is equal to our average heading. We're going to summate that plus our linear velocity, or normalized linear velocity, which is our heading. And then so now that's going to satisfy condition number 2. Well, this isn't complete yet, but this is our alignment. This is where we're handling our alignment. So outside of our loop of looping over our neighbors, we've only summated this up. Now we have to do the actual division to take the average. And to do that, we're just going to say v average heading is equal to v average heading divided by our table. That's the total number of elements in our flock, because we're looking at every other element. Table. Minus 1, because we're not looking at ourself, right? So we want to make sure our average is accurate. Since we're skipping ourself, we're basically skipping one element in this table, so we've got to make sure, since we're adding up only the elements that are our neighbors, we just got to make sure we subtract that out before we do the division to take the average. And the last thing we're going to do is we're going to normalize this as well. And this is important because our heading is, when we take an average of a bunch of different headings, it's not going to necessarily be inside a unit vector. So it's going to be like a skewed direction, basically. Normalizing will kind of make sure it's in a unit sphere. So now we have our average heading of our system. And so again, just like we did up here, we got our rigid body and we applied an impulse to kind of move away from our neighbors. We're going to now add an impulse that kind of moves us toward the direction of the heading. And so we're just going to apply a central impulse. That's our heading. That's our normalized value. Times a scalar, or time scalar. Actually, I'm going to rename this to time scalar. That's our ensures that it's always normalized given our frame rate. And then minus some value, which we're going to tweak in a second, depending on how this behaves. Okay, so let's see what happens if we hit play. So they all kind of move up, and the reason why is that initially they're all bumped up slightly, and so since they're all kind of moving up, they all kind of did that. Now if we make it float, there must have been just a little bit of motion in that direction, so then they all kind of started moving that direction. What I'm going to do is I'm just going to like select them now and grab a bunch, move that in the opposite direction, and then they all start moving that direction. If I grab them, move these 4 in that direction, that's enough to kind of skew the average in that direction. You'll notice that the other ones are kind of like, oh, they're all moving this direction, so I'm going to start to follow those other 4 in this case. And it's the average, so it's like wherever the other ones are. So if I make this, eventually they will reach. So now they kind of look at where those average headings are, and they stay in that direction basically. And as that direction is changed, if let's say something gets in the way, and I can build like a box here, I'll make this fixed. Our flock, as it hits that box, they're all going to start to, the headings are all going to get kind of interrupted by the box, so those linear velocities are going to get interrupted, and then they should adapt accordingly. So they're going to move there, and then, oh, heading's interrupted, so they're now moving kind of sideways away from that box. So it's a neat way of also making their way around collision obstructions in the space. All right, so we've satisfied number 2 of our Wikipedia article on flocking. Number 3 is cohesion. Steer towards the average position of the neighbors. Long-range attraction. So to do that, we know everything to do this now. I'm going to go back into the code, and we're going to, in the same way we took an average heading, we're going to calculate our average position. That's going to be the centroid of our flock, right? Where the average position of all of these things is. It's some value that's going to be in the middle of all of them. So I'm going to do 3 cohesion. And so to do this, again, just like we took an average for the heading, I'm going to initialize up here our centroid. Initialize that to 0, 0, just 0, and then every single time we're going to say our v centroid is equal to our v centroid plus our element, our neighbor, its world position, right? So that we're adding up whatever the positions are, and then we're going to take the average, and that will give us our nice centroid or center position of that system. So just like we did here, outside of our neighbor loop, v centroid is equal to v centroid divided by, again, the total number of elements in our table minus 1 for ourself. That's our center point. And now, given the center point, we have to move toward it, right? Steer towards the average position. So we have to calculate our steering direction to move toward our centroid. So it's similar to this avoiding what we did up here for separation. You know, we have to take our world position and subtract it from that centroid. Or actually, the centroid subtracted from the world position, and then we'll steer toward it. Our position minus the centroid. So we're going to say our steering direction is equal to our world position. Get our world position minus our centroid. And once again, when we do that, it's going to have magnitude, which we want to squash out. We just are interested in the direction, and then we'll use our own magnitude to control for the speed. So I'm just going to set I'm going to normalize our steering direction here. Normalize. And finally, just like we did with this, we're going to add an impulse to kind of move it with respect to that steering direction. Time scaler, and then some value that we're going to play around with. So that I think makes sense. Let's go ahead and take a look here. So now they're going to, oops, they're moving in the opposite direction. I was wrong. I need to invert this. So we're moving toward the centroid, so it's centroid minus that. I always get that wrong. Okay, so let's see what happens. They're all going to now bunch near each other. They're going to avoid, and they're kind of move in the direction that the rest are now moving. So they hit that. Now they're going to move sideways, and now they're always kind of moving up. So we now have kind of an interesting flocking behavior. So we're going to keep tweaking some of these numbers. We can certainly tweak the radius to ensure maybe they don't overlap as much. We can tweak these other three values: the separation value, the average heading, the heading of the thing that the impulse that we inject to make a move in that average heading, and this centroid impulse. And well, let's see what we can get here. So they're kind of clustering together. What if they more aggressively move toward that? Maybe not. Maybe we'll make this a little weaker, the clustering. No, they kind of weakly cluster, but they're more strongly about that. It's the kind of thing that we'll be able to tweak when we create more. So let's go ahead and create more. So I'm going to go into this flock here. I'm going to just make more shared copies of these. So again, shared copies, Control-Alt, not Alt, to ensure that the script is shared, so we can just make changes to one, and then it adjusts in all of them. Okay, so let's see what happens. So now we get more interesting flocking behavior as they hit and kind of swarm a little bit, kind of moving fast in that one direction. So I'm going to slow down some of these. The other thing we could also do is just crank up their mass a little bit, because we're not factoring in their mass, and so the forces are going to be relative to that. So now they're a little bit slower. Maybe we'll reduce that a little bit. And so another thing you might have noticed is, as I made more copies of these things, it's gotten a little bit slow. Maybe it's harder to see on the stream, but the frame rate has gotten a little worse on these all of a sudden. And in part, this is related to the fact that this code is running kind of inside a Lua layer that runs on top of native code. But another reason why is, if we keep reading this flocking rules Wikipedia article, and if we go look at this algorithmic complexity, we're going to see that a basic implementation of flocking algorithm has a complexity of O(n)². And so now, why is that O(n)²? Big O notation is what that's referred to as. So the question is why is the complexity of this n²? Well, the reason why is that, imagine every frame we're visiting each one of these spheres to kind of update its behavior with respect to its neighbors and this flocking algorithm. For each one, it's going to loop in this loop looking at all of its other neighbors. So whatever the total count of items is inside here, we're basically going to square that. The total number of instructions that are running inside this inner loop here is going to be equal to the total number squared of these, right? And so that's going to get kind of expensive very quickly. And so we need to try to figure out a way to optimize for this a little bit, so that we can create more, because obviously flocks are really nice when we have a lot of elements, and then that's when you really start seeing that complex behavior. But to start, this is a good way to look at it, to begin with. We're like, oh, well, now this is our pure kind of implementation of it, and we can tweak and use this as our kind of gold standard to kind of derive our optimized solution from. It's always best to start with your pure implementation if you can, because it lets you really understand the kind of purity of an algorithm, and then we can start to optimize afterwards. So the big optimization that we can do, there's actually two big optimizations that we can do here. The big one that we really need to solve is trying to figure out a different way of doing separation that's a little bit more efficient. The other parts are actually quite straightforward, the alignment and cohesion. So in other words, calculating the average heading and calculating the centroid, we don't really need to do that for every object. We can just do it once every frame, so that once we've calculated the centroid of the overall, we don't need each person to individually calculate that. We can just do that once, and same with the average heading. So this is a good candidate for centralizing, to move out and doing that once per frame. Remember, this is happening per object per frame. So if we pull some of this out, we'll be able to do it once per frame. So let's create a centralized script so that we can do that inside there. So to do that, I'm just going to, on our train space inside here in the browser, right-click. I'm going to create a new global script. And I'm going to call this our flock manager. And in here, just like we did, we're going to implement this onTick function. So this is going to get called every frame. The difference being it's only going to get called once per frame for this one flock manager. So I'm going to do onTick for this. And so now in here, we're going to move some of the code that lives inside these individual elements into this function here. So I'm going to edit this code here. I'm just going to copy all of this, and then we will all this inner part, and then we'll pull out the code that looks at our flock from inside here. Okay, so this is obviously the code that we would normally run inside the element, so we're going to have to mutate it a little bit. So the first thing we want to do is we can't look at our parent now, because obviously this is a script that lives inside the library. Its parent node doesn't make sense anymore. We actually have to drag and drop in our flock into here. This is now the equivalent of what we were doing before to get the parent node. This will be the node whose children are all the elements in our flock. So we're going to store that inside here. And we're not going to do the separation logic inside here. We're going to still have to do that per object. So we're going to erase that. We have to remove this don't consider ourself logic, because now we're just looking at all of our children. So that's removed. And I think now we have everything we need to calculate this. So for every element in our flock now, we're going to calculate our average heading and our average and the average location, the centroid of it. And we're not going to inject any of those impulses in here. We're going to do that outside. And so we're going to have to remove all that. And then we don't need this radius here. We don't need this. We're not injecting impulses here. So now this code, we've pulled that part out of that other code, so that we're now calculating the alignment once per frame and this cohesion centroid once per frame. And the other thing we'll do to make this a little cleaner is because we're going to access this object from the individual elements. We're just going to create accessor functions to get that information of what we just computed. So I'm just going to say get our average heading. We're going to call this function to return this value that we calculate inside here. It's equal to v_av heading. And function global script get our centroid. Return our centroids. This is just returning those variables that we just calculated inside here. And we're going to initialize these as well up here, our v_av heading, just in case we call this before this tick function gets called. We just want to make sure that they have something valid inside them so it doesn't throw an error. Centroid vector 3, 0, 0. Okay. So this will calculate this. We've got to reset these every frame, because we're calculating that average. We calculate that average. Oh, that's right. We don't need to subtract 1 here from the table count, since we need to consider every element now. So this will now calculate the average heading of all of our elements and the centroid of all of them, and then we can call these functions on this object to get that information that's calculated inside here. Okay, so let's go back into our individual element script. We can now pull out some of the stuff in this loop. We don't need to do that there anymore, which is nice. And so we don't need to calculate that here. And what else? We don't need to do that here. So now we can just drag and drop this flock manager where that code lives. We're just going to drag and drop that in here, and we can just query the flock manager for that average heading. And here we're going to say get our average heading. That's that function that we just wrote that returns that. It's going to take that average heading and apply our impulses per object in here, and then the steering direction, we need that centroid. Get our centroid from there. And it's going to normalize that, and voila, we now have this centralized location is calculating this. And let's go ahead and see what happens if we hit play. It's a little bit better. Frame rate's slightly better. Good, not great. We still have some optimizations to do, but it's getting better. So I'm going to throw these in this direction. They're all going to kind of move in that direction, move in that direction. And there they go, flocking together. Okay, so we've made some optimizations here, but it would still be nice if we could eliminate this having to look at every single neighbor. That's your classic kind of brute force way of doing something. And so can we reduce that? Well, yeah, we can. There's a couple ways we can consider this. So one way to reduce this is to use our neighborhood graph. So the way 3D engines work is, in Simmetri has this as well, it manages objects inside a space by kind of storing them in these structures that are kind of spatially organized. So given a point in space, you can kind of ask the engine, give me objects that are kind of near this point in space, and depending on how it stores that space. Classic ways are binary space partitions or octrees. Lots of different ways you can kind of store objects in space. Given these structures, you can kind of ask in a faster time. You can basically gather all of their neighbors. You can collect objects inside the space in a much faster time than having to consider every object. You don't have to loop over every object in the space. You can just kind of say, okay, is it in this kind of region of space? I know that we're kind of in this region of space. Get me all the people that are also within this region of space, all the objects. So how do we access that? Well, we're going to call self-get-space, get our entity space map. That's our space maps are these kind of these neighborhood structured systems that let us find things. And we're going to call this function called find intersecting nodes. And so it's basically going to search the space in a more efficient way. And the first parameter it needs is a primitive. It's a shape, a volume basically, that it's going to search. And that's going to just be our, I'll explain this in a second, world position. It's going to be a sphere that's going to use our radius and this world position. So basically it's that bubble of radius that's determining if our objects are colliding or not. It's going to search that radius and it's going to gather all the objects that intersect that. And it's going to return them inside a table, which we can just use the same table that we use here. So instead of getting all the nodes now, we're going to actually, using this kind of searching system, we're simply going to return the elements that intersect the sphere in that table. So we're going to just get the elements that happen to be kind of surrounding us within that radius. So now we're only going to consider those. We still have to filter ourselves out because we will be part of that. But now we'll only consider those immediate neighbors by having searched this more efficient kind of searching system via this more efficient searching system. So let's see what happens if we hit play. So they're still avoiding, and notice that now it's much smoother, it's much faster. They're avoiding each other, they're getting their neighbors, moving away, but it's much, much more efficient. So now we can go ahead and create more copies of objects. So I'm just going to I'm going to hold down Control-Alt, and I'm going to make shared copies of all these. And so now we have a lot more. And the forces here are still kind of a little bit too fast for my taste here. I want to slow these down just a little bit. Let's see here. Well, one of the things that we can do is we can, originally on the constant force on this individual flock element, we set we added a force that kind of counteracted gravity, so this is why they're very floaty. I'm just going to reduce that force so that gravity now has a little bit of influence on the object, so they stay kind of grounded, and then they bounce, and they still have enough force to override it. So we can also keep tweaking these scalars here. So maybe we won't go as much on that. Maybe a little bit more on that. There we go. So now they're a little bit more on the ground. Maybe we'll keep increasing that force. Now it looks like a swarm of bees. I'm going to still make gravity have a little bit more influence here, so we're not going to counteract as much on the gravity front. I'm going to keep increasing that. Okay, so they don't fly away like that. Now gravity has a lot more influence, so they're going to come back down to the ground here and see what they do when they hit the ground. Kind of like now fight each other, and now they kind of crawl on the ground, which is kind of interesting as they fight. Fight. Okay, stop. Let's build a little environment for these things so that we can kind of observe what they do. I'm just going to zoom all the way out here and go to the terrain. I'm just going to build a little space for them. So now they have some stuff to contend with. They don't get off easy. Okay, so let's see what happens when we hit play here. They flock together, and then they decide, oh, let's go over here. They kind of started going that one average heading. They almost look like an amoeba here. They're kind of crawling over one another. Now they're going to crawl up this. They're going to slowly start having those headings heading vertical. So they now kind of all average themselves out over there. They're going to crawl over this space here. Eventually they make it over the hill and they're free. Okay, so that's pretty cool. We can do another thing. So these are just orbs, magical orbs that kind of float. In the example that I was showing in the beginning, what we build up to, I was actually showing a cone so that we can kind of see which direction they're moving. So what I'm going to do is I'm going to delete all the -1, and we're going to change this a little bit. instead of using a sphere, we're going to keep our sphere, but we're going to make it invisible, and then we're going to stick on them a cone that we're going to face in the direction that they're all moving. We're going to face it toward the direction of the heading. So I'm going to go into our flock here. I'm just going to delete them all -1. I'm just going to do that via this thing here. And we're back down to our individual element. So now I'm going to create our cone. This is going to be like our thing that's going to point in the direction we're moving, because it looks a little bit more realistic. I'm just going to draw a cone up, and I'm going to have it collapse down to a point. And I'm going to remove the rigid body of this cone, because we don't want this thing to have physics. This is just strictly an adornment on the object that we're just going to kind of control absolutely. And we're going to make this a child of our elements. So the cone is going to be a child of our sphere. So it's going to move exactly where our sphere goes. And I'm going to set this, I selected that child. I'm going to zero out its transform. I clicked on its transform. That ensures it goes exactly in the center of our sphere. And the other thing we're going to want to do is our cone, by default, when it has no rotation, it looks upwards. It doesn't look in the look at direction. So our look at direction, we can use a function in script saying is look at, basically. And when we call that function, it will align the object to face a particular direction we give it. The problem is by default, a cone is orientated to look upwards. So we need to add a 90-degree rotation so that it faces the same direction we expect our look at direction to do. And we go into this a little bit in previous tutorials, but I'll try to explain it a little bit better once we do this. So the other thing, actually, before we do that, let me remove the material from our sphere. We don't want to see our sphere anymore. Our cone is now the thing that's going to represent our bird or herd item. So I'm just going to remove from our sphere, I'm just going to remove its material. I'm just going to set its material to none. It becomes invisible. So now we just see our cone. So if I would hit present, we wouldn't even see this slightly darkened sphere. That's just there so we can kind of see it in the editor, but that would disappear as well. So the facing direction now of our cone is up, and we need to rotate that 90 degrees. So we're going to do that by clicking on the cone entity. We're going to go to the mesh modifiers, and I'm going to add a new vertex transform. And what this does basically is it rotates the vertex data itself. So like we've now redefined our cone so that it actually faces this direction, the direction that correlates with the z-axis of our object. So notice that before I made that change, I'm just going to delete this. If we moved along the z-axis, which is what's referred to our look at direction, that's our look at axis, it's moving it's moving perpendicular to our looking up direction, and so that's why we want to rotate. We want to apply this little trick here, this vertex transform, so that it will transform along the same direction it's pointing. So now when we call look at, it will look at the same direction that our cone points. Hopefully this will make more sense when we set this up. So our cone is now faced. I'm just going to increase the radius of our sphere just a little bit so it envelops our cone so that things don't overlap just slightly. There we go. So now our cone is kind of included inside the sphere. And so if we hit play, nothing much will have changed here. It will still kind of move around like that. But now what we can do is we can adjust our cone to face the heading direction. So I'm going to go back into our script here. And I'm going to, here we're going to just find our cone, self::find node. Remember, we're at this level here, we're at the element level, so we got to find our child cone entity here. Find node by name, and it's called cone entity. We can call that whatever we want, but that's going to store that in a variable called cone, and then we're just going to say cone look at, and we're going to look at a particular point in space. Now, we want it to look down the direction of the heading, so we don't want to look necessarily at a point in space. We kind of want to look forward, but because look at requires a point in space, we're just going to have to project out a far away distance, and we'll look at that distance. And so we're going to look at we're going to take our current position, get our world position, and we're going to project it along our average heading, right? That's where everybody's facing. That's the facing direction. So we're basically taking our current position, and we're going to add that average heading, which is going to be a point in front of us. And then we're going to multiply this by a large number. And the reason why is, again, we don't want it to point at a point right in front of us. We want it to kind of point far, far away, far down the distance of where our average heading is facing. And then that'll achieve that. Essentially makes it so far away that effectively it's as if they're looking straight ahead along the axis of the heading. So let's see what happens when we hit play. So now it's moving down. It now will always face whatever direction it's moving. So if I grab it and move in this direction, you'll notice that whatever direction I accelerate it, it kind of looks in that direction. So let's go ahead and go back and make some shared copies of this parent element inside this flock here. I'm going to hold on. Make sure you don't make, if you're out at this level, make sure you don't make shared copies of the flock. Double click on the flock so that we're only making sure we're inside it and making copies of the element inside it. Or else, if you make copies of the flock, they're all going to have, it's not going to, our flock manager is only going to look at one of them and it's not going to look right. So I'm inside this flock node by double clicking at it like this, and then I'm making copies of it. Control Alt copies of it here. I'm going to select those four. I'm going to make copies of that. Select all those. I'm going to make copies of that. I'm going to select all those. I'm going to make copies of that. And maybe we'll select all those and make copies of that. And so let's see what happens. Now they all kind of look down. Now they're all kind of trying to go up. And now they're all going to kind of move in that direction. So now they're kind of facing the direction that they're all trying to go. So it's a little bit more realistic. Some of them are fighting each other. So we can do one more thing here to efficientize this. Oh, the other thing we can do here is instead of having them all face that direction by default, we can actually have them like just add a little bit of randomness to their initial positions here. I'm going to rotate these, maybe facing that direction. Rotate these facing this direction. Those are over here. Maybe these are over here facing that direction. These are over here. These are over here facing this direction, and so forth. So now they're all going to, because of the flocking behavior, the first thing they're going to do is they're going to find each other. It's going to all flock to that centroid, that center average position, and they're all going to kind of decide where to go, and then move in that overall position. So there they go. Now, one other efficiency we can do, because I'm already starting to see that the frame rate is going just a little bit, dropping again a little bit, is let's do one more optimization so we can make even more copies of these objects. So again, what we're doing right now is for every element we're asking that more efficient structure to find intersecting objects. We're gathering all of our neighbors. But you know what? Our physics engine effectively already does that, and it happens all natively. So right here we're crossing that native Lua boundary by calling this function, getting a small collection of objects and then running running Lua code on it. If we just let the physics engine essentially already handles collision, right, to make sure they don't overlap, if we're happy with that, then we can remove this basically. And the idea being that the collision occurring at the physics level is good enough, right? It ensures that they don't overlap each other. Sure, they don't push away from each other at that point. They're just simply kind of reflecting off each other. We can make them a little bouncy maybe so that they bounce off of each other, but it's not quite as realistic. But by removing this, we're making it even more efficient. So now we're just basically saying, physics, you take over making sure they don't overlap, which it already does. And we can actually control now that radius distance by just cranking up that radius of that sphere, right? So I'm just going to go into this element. I'm going to just crank up the sphere shape radius, and now there's less overlap, right? Now they don't try to overlap as much, but they still kind of bump into each other a little strange looking. But if we're okay with that, with this optimization, now we can even make even more copies. So I'm going to go into the flock here, and I'm just going to make even more copies, shared copies of these, because it's even more efficient now. And so now we can make even more here without it getting too slow. And by the way, it'll get even more efficient if we were to export this as an application. Because the editor has to maintain a bunch of state regarding undo and this and that, it's going to be a little bit more taxing. Once we export this as an application, it'll run even better. So you get at least a 20% performance improvement. But now we have this nice kind of satisfying size swarm that kind of make their way up these hills and do all sorts of interesting things. And I'm going to maybe knock down the radius a little bit, make them, the smaller this radius, the more they kind of compact toward each other. So you get these interesting behaviors, like now they're like fighting each other in this like weird amoeba-like swarm. And it's fun to give them like obstacles, like okay, you give them a giant sphere obstacle here, and now they hit it, and then they make their way around it in this kind of interesting way. Maybe you make the radius slightly bigger, so they're a little bit more avoidant of one another. What else can we do? We can keep tweaking those. Since these are all shared copies, we just can tweak one of them here, and it'll apply to all of them. So this radius is now not being used here, so we can mark this, make it a little clearer. It's using just the physics radius to collide with one another. So let's crank up their average heading, the forces that we're using to maintain the average heading. So what if that was much stronger? What would that do? Now they much faster will try to all go in some direction. A little bit more bird-like almost. And now they're going to reassemble themselves to that average position and kind of make their way, and they're much more swarmy now and scary looking, more like bees or something. Now they're going to go up. Now gravity is going to eventually they're not going to be able to fight that constant force. They're going to make their way back down, These look like more like bees now. So it's fun to tweak those. There's all sorts of possibilities that we can do there. And then, it's always fun to enable maybe depth of field. And then you can kind of watch them. Oh, one other thing we could do is, well, let's say you want to control. Right now, they're not controlling. We're not really controlling where they go. They just have a mind of their own. We can control them maybe by blocking them, and then they eventually figure out a new heading and go that way. But if, let's say we wanted to have them go to a particular place, like wherever I click the mouse or hit the laser on the ground, we want them to fly to that location. Well, to do that, what we're going to do is we're going to go back into the flock manager, this code here, and right now it's calculating this centroid. But let's add a function that lets us explicitly set that centroid location. So instead of it being calculated based on the center point, I'm just going to basically create a function that lets us set it explicitly. So centroid, we're going to pass in a vector, and we're going to set our centroid equal to that vector. So now if we call this function, we can kind of override its calculation of the centroid, and we'll set the centroid to that. So then when those individual elements query us via this getCentroid, they're going to return our explicitly set centroid. So now we just need a way of setting it based on a position. So I can actually just create a sphere here. This will represent our swarm location, our centroid that they're going to fly to. I'm going to change its color. I'm going to remove its, I'm actually going to make its movability on its rigid body to fixed, false. And the last thing we're going to have to do is we just need to go into this flock manager. Actually, we can do it from inside the flock manager. Actually, let's make it, yeah, let's do it inside the flock manager. So inside here, instead of setting the centroid equal to that here, we're going to override it. We're going to say, we're going to drag and drop in that sphere entity we just created. I'm going to rename this to something a little bit better. This is going to be our flock target. I'm going to drag and drop this flock target icon right into our script here, and we're going to set our centroid, the centroid, equal to that thing's world position. And the other thing we could do, just make it a little bit more flexible, is we can say if our flock target is active. So that means we can if we deactivate that node, they'll go back to just flocking in whatever direction, wherever they happen to be. So flock target dot active, only if it's true do we override that centroid to that. So now we have a place that they all go to. So we did not use the set centroid function, by the way. I just decided in the end just to do it all inside here. Now they're going to make their way toward this red thing instead, or at least try if they can override gravity. Oh, now they've overshot it. So eventually those forces will take over, and it might be that the heading force is too strong for them. Nope, here they go. So eventually that centroid force is overriding it. Now the heading force is too strong. That's right, it is much stronger, the heading force. So let's go ahead and make sure that the heading force is a little bit weaker than our centroid force. I'm just going to go in here. Our heading force is 0.7. I'm going to make this 0.3, and I'm going to make our centroid force 0.7. So now they're that force is stronger. So eventually it's going to override their, and you'll see them all turn now. And here they go. They're making their way toward this red thing here. And they're going to swarm around this. So as we move this around, you can see them all trying to make their way there. And eventually if you put it in the middle, they'll kind of like stick around that location. So now you can stick this on your player. Let's say we have our car here. I'm going to create an actor here. I'm going to stick our car in here. Actually, let's stick it on a little copter. This is our little like drone, and we can have them follow our drone. So I'm going to just take this. I'm going to remove its rigid body so that it doesn't fight the drone's rigid body, and I'm just going to stick it on the drone here, right on the mini copter that way. I'm going to just set its origin to 0, so it's actually on the drone. And I'm going to just set it to be a little bit smaller. So now if we control this drone, let's see what I have the settings bound as here. Let's see, I don't remember what this is bound. Flying controls, ascend, controller not connected. So spacebar will ascend. Ascend will be alt. We'll use these 4 keys to go with that. Bank left, bank right. Okay, let's see. Now they're going to follow me. I'm like their leader. I'm going to increase its power a little bit. Lift force will make it a little stronger. And now they're going to attempt to follow this thing here. And now we can kind of guide them to wherever we want here. And I'm going to add to the camera, I'm going to add camera tracking. So we track our node here. And now we can watch our swarm. If I hide those things, follow our little drone copter here. Or at least kind of attempt to. And again, by tweaking those forces, we can make them a lot more aggressive so they follow it a lot better. Okay, I'm going to remove, again, that default camera, that tracking player controller, so I can freely move here. So that's about it. So hopefully I will share this up on Steam, and I'll stick in the Discord channel. And if you're joining us outside of Discord, don't forget you can join our Discord channel by clicking on Learn and join the Symmetry Discord channel. If you're new to Symmetry, be sure to do Intro to Basics and go work through all these interactive tutorials. They'll teach you how to kind of move the camera and make all those kind of movements that you might otherwise want to do if you were kind of the kind of things you need to know how to do, which I've kind of glossed over here. I hope you guys enjoyed this. I'll quickly check to see if anybody new to it was asked questions. But it looks like this will have to, we'll answer your questions after this. Well, I'll stop the stream to like kind of close this video officially, and then if anybody has questions, I'm glad to open it up and tweak away. Thanks for watching, and I'll see you next time.